According to the Rhode Island Building Code, which adopts the 2018 International Building Code, WIG, Section 404.3 requires light switches to be installed at all required exits and other locations where specifically required. National Electrical Code, or NEC, Section 404.2 requires light switches to be located so that a person can enter a space and activate the lighting without moving more than 20 feet or 6.1 meters. While the IBC is the baseline for both commercial and residential buildings, there are some differences in the requirements. However, the provision requiring light switches at entrances to a room is not one of the differences. Light switches should be installed at both entrances to the room, regardless of whether the building is commercial or residential, based on the IBC and NEC. Consider installing a three-way switch system, which would allow for lights to be turned on and off from either entrance. This would meet the code requirements while providing the desired functionality. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for electrical installations in buildings. It's updated every 3 years and adopted by most jurisdictions in the United States to ensure electrical safety. Article 90 covers the purpose, scope, enforcement, and definitions related to the NEC. Chapter 1 contains general requirements for electrical installations, including wiring methods, overcurrent protection, grounding, and bonding. Chapter 2 focuses on wiring and protection, detailing requirements for conductors, cables, raceways, and overcurrent protection devices. Chapter 3 covers wiring methods and materials, specifying approved wiring methods for different applications and environments. Chapter 4 addresses equipment for general use, including receptacles, switches, lighting fixtures, and appliances. Chapter 5 covers special occupancies, such as hazardous locations, healthcare facilities, and places of assembly, with specific requirements for each. Chapter 6 deals with special equipment, including electrical signs, elevators, and electric vehicles, outlining installation and safety standards. Chapter 7 focuses on special conditions, such as emergency systems, fire alarm systems, and critical operations power systems, with requirements for reliability and performance. Chapter 8 is dedicated to communications systems, including telephone, data, and CAT-TV wiring, with requirements for separation from power conductors. Chapter 9 contains tables and examples used for calculating conductor sizes, raceway fill, and other electrical parameters. Understanding these chapters is crucial for ensuring safe and compliant electrical installations. When planning an electrical installation, several factors must be considered to ensure safety and compliance with the NEC. Firstly, determine the load requirements of the electrical system, including the total amperage and voltage needed for all connected devices and appliances. Secondly, select appropriate wiring methods and materials based on the environment and application, considering factors like temperature, moisture, and corrosive substances. Thirdly, ensure proper overcurrent protection by installing circuit breakers or fuses with the correct ampacity to protect against overloads and short circuits. Fourthly, implement effective grounding and bonding techniques to minimize the risk of electric shock and ensure a safe path for fault currents. Fifthly, adhere to all applicable codes and standards, including the NEC and local building codes, to ensure compliance and safety. Sixthly, consider future expansion and flexibility by designing the electrical system with sufficient capacity and spare circuits to accommodate future needs. Finally, document the electrical installation thoroughly, including wiring diagrams, panel schedules, and equipment specifications for future reference and maintenance. These considerations are essential for creating a safe, reliable, and compliant electrical system. The International Building Code, or IC, is a model building code developed by the International Code Council, or IC. It provides minimum requirements for building systems using prescriptive and performance-related provisions. It addresses structural, fire safety, and means of egress, among other things. Chapter 1 of the IBC covers the scope and administration of the code, including its purpose, application, and enforcement. Chapter 2 provides definitions of terms used throughout the code. Chapter 3 classifies buildings based on occupancy and use, which affects the required fire resistance, means of egress, and other safety features. Chapter 4 addresses special detailed requirements based on use and occupancy, such as high-rise buildings, atriums, and underground structures. Chapter 5 specifies general building heights and area limitations based on occupancy and construction type. Chapter 6 deals with types of construction, classifying buildings based on fire resistance and materials used. Chapter 7 covers fire and smoke protection features, including fire-resistant construction, fire stopping, and smoke barriers. Chapter 8 addresses interior finishes, regulating the use of combustible materials on walls, ceilings, and floors. Chapter 9 covers fire protection systems, including fire alarms, sprinkler systems, and standpipes. Chapter 10 focuses on means of egress, ensuring safe and accessible exit routes from buildings. Chapter 11 addresses accessibility, ensuring that buildings are usable by people with disabilities. Chapter 12 covers interior environment, regulating ventilation, lighting, and sanitation. Chapter 13 addresses energy efficiency, setting requirements for building envelopes and mechanical systems. Chapter 14 covers exterior walls, regulating the use of combustible materials and fire resistance. Chapter 15 addresses roof assemblies and rooftop structures, ensuring fire resistance and structural integrity. Chapter 16 covers structural design, including load requirements and material standards. Chapter 17 addresses special inspections and tests, ensuring that construction meets the code requirements. Chapter 18 covers soils and foundations, ensuring stability and load-bearing capacity. Chapter 19 addresses concrete, specifying material standards and construction requirements. Chapter 20 covers aluminum, specifying material standards and construction requirements. Chapter 21 addresses masonry, specifying material standards and construction requirements. Chapter 22 covers steel, specifying material standards and construction requirements. Chapter 23 addresses wood, specifying material standards and construction requirements. Chapter 24 covers glass and glazing, ensuring safety and energy efficiency. Chapter 25 addresses gypsum board and plaster, specifying material standards and installation requirements. Chapter 26 addresses plastic, specifying material standards and permitted uses. Chapter 27 addresses electrical, referring to the National Electrical Code, or NEC, for electrical systems requirements. Chapter 28 addresses mechanical systems, including heating, ventilation, and air conditioning. Chapter 29 addresses plumbing systems, including water supply, drainage, and sanitation. Chapter 30 addresses elevators and conveying systems, ensuring safety and accessibility. Chapter 31 addresses special construction, such as temporary structures and swimming pools. Chapter 32 addresses encroachments into the public right-of-way, regulating structures that extend beyond property lines. Chapter 33 addresses safeguards during construction, ensuring safety for workers and the public. Chapter 34 addresses existing buildings, regulating alterations and additions. Chapter 35 addresses reference standards, listing the standards that are referenced throughout the code. These chapters provide a comprehensive set of requirements for building design and construction. A three-way switch system is a common electrical circuit that allows a light fixture to be controlled from two different locations. It uses two three-way switches, which have three terminals each, connected in a specific way to achieve this functionality. The basic components of a three-way switch system include firstly, two three-way switches, secondly, a power source, typically a 120 volts alternating current, or volts AC, circuit, thirdly, the light fixture being controlled, fourthly, wiring to connect all the components. The wiring configuration of a three-way switch system involves firstly connecting the power source to the common terminal of one of the three-way switches, secondly, running two traveler wires between the two three-way switches connecting to the traveler terminals on each switch, thirdly, connecting the common terminal of the second three-way switch to the light fixture, fourthly, connecting the neutral wire from the power source directly to the light fixture. The operation of a three-way switch system is based on changing the position of the switches to complete or interrupt the circuit to the light fixture. When both switches are in positions that complete the circuit, the light is on. When either switch is flipped to the opposite position, the circuit is broken and the light turns off. Flipping either switch again will toggle the light state. Common applications of three-way switch systems include firstly, hallways, where lights can be turned on or off from either end. Secondly, staircases, where lights can be controlled from both the top and bottom. Thirdly, large rooms with multiple entrances, as in the scenario described earlier. Fourthly, bedrooms, where lights can be controlled from both the door and the bedside. When installing a three-way switch system, safety precautions are crucial. Firstly, always turn off the power to the circuit at the circuit breaker before working on any wiring. Secondly, use appropriate personal protective equipment, such as insulated gloves and safety glasses. Thirdly, carefully identify and label all wires before disconnecting them. Fourthly, follow the correct wiring diagram to ensure proper connections. Fifthly, use wire connectors or other approved methods to make secure connections. Sixthly, test the circuit after installation to verify that it is working correctly. Troubleshooting a three-way switch system may involve firstly, checking the wiring connections to ensure they are secure and correct. Secondly, testing the switches to ensure they are functioning properly. Thirdly, using a multimeter to check for voltage and continuity in the circuit. Fourthly, replacing any faulty components such as switches or wiring. Fifthly, consulting with a qualified electrician if the problem cannot be resolved. Understanding the components, wiring, and operation of a three-way switch system is essential for safe and effective installation and troubleshooting. Proper planning and adherence to safety guidelines are crucial for ensuring a reliable and compliant electrical installation. When installing electrical wiring, several important considerations must be taken into account to ensure safety, compliance, and optimal performance. Firstly, conductor size is critical, and it must be selected based on the ampacity requirements of the circuit. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and installation method. Secondly, overcurrent protection, such as circuit breakers or fuses, is essential to protect against overloads and short circuits. The overcurrent protection device must be sized appropriately for the conductor ampacity and the load requirements of the circuit. Thirdly, grounding and bonding are crucial for minimizing the risk of electric shock and ensuring a safe path for fault currents. The grounding system must be properly installed and connected to all metal enclosures and equipment. Fourthly, wiring methods must be selected based on the environment and application. The NEC specifies approved wiring methods for different locations, such as dry, damp, and wet environments, as well as for different types of occupancies. Fifthly, box fill calculations are necessary to ensure that electrical boxes are not overcrowded with conductors and devices. The NEC provides rules for calculating the maximum number of conductors allowed in a box based on its size and type. Sixthly, voltage drop must be considered to ensure that the voltage at the load is within acceptable limits. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Seventhly, conductor identification is important for proper wiring and troubleshooting. The NEC requires specific color codes for identifying different types of conductors, such as hot, neutral, and ground wires. Eighthly, workmanship is essential for a safe and reliable electrical installation. All connections must be made securely and neatly, and all wiring must be installed in accordance with the NEC and local codes. Ninthly, inspections are required to verify that the electrical installation meets the code requirements. A qualified electrical inspector will review the installation and identify any deficiencies that must be corrected. Finally, documentation is important for future reference and maintenance. Wiring diagrams, panel schedules, and equipment specifications should be kept on file for all electrical installations. These considerations are essential for ensuring a safe, reliable, and compliant electrical installation. Understanding the different types of electrical boxes and their applications is important for proper wiring and safety. Firstly, metal boxes are commonly used for housing electrical connections and devices. They provide good protection against physical damage and are suitable for use in exposed locations. Secondly, non-metallic boxes, typically made of plastic, are lightweight and corrosion resistant. They are suitable for use in damp or wet locations and are often used for residential wiring. Thirdly, junction boxes are used to splice or terminate multiple conductors. They provide a safe and accessible enclosure for making electrical connections. Fourthly, outlet boxes are used to mount receptacles, switches, and other devices. They are typically installed in walls or ceilings and provide a secure mounting point for the devices. Fifthly, switch boxes are similar to outlet boxes but are specifically designed for mounting switches. They typically have a smaller capacity than outlet boxes and are designed to accommodate the wiring for a single switch. Sixthly, weatherproof boxes are designed for use in outdoor or wet locations. They provide a watertight seal to protect electrical connections and devices from moisture and corrosion. Seventhly, floor boxes are designed for use in floors and provide a recessed enclosure for receptacles or other devices. They are typically used in commercial or industrial settings where receptacles are needed in the floor. Eighthly, extension rings are used to increase the capacity of an existing electrical box. They are installed between the box and the device and provide additional space for wiring. When selecting an electrical box, it is important to consider the size and type of conductors being used, the number of devices being installed, and the environment in which the box will be located. The NEC provides rules for calculating the minimum size of electrical boxes based on the number and size of conductors in devices. Proper selection and installation of electrical boxes are essential for ensuring a safe and compliant electrical installation. Understanding the different types of wiring methods and their applications is crucial for safe and compliant electrical installations. Firstly, non-metallic sheath cable, or NM cable, is commonly used for residential wiring. It consists of two or more insulated conductors enclosed in a non-metallic sheath. It is suitable for use in dry locations and is relatively easy to install. Secondly, metallic sheath cable, or MC cable, is similar to NM cable but has a metallic sheath for added protection. It is suitable for use in exposed locations and can provide better protection against physical damage. Thirdly, electrical metallic tubing, or EMT, is a thin-walled metal conduit that is used to protect conductors. It is suitable for use in both exposed and concealed locations and can be easily bent and cut to fit the installation requirements. Fourthly, rigid metal conduit, or RMC, is a thick-walled metal conduit that provides excellent protection for conductors. It is suitable for use in harsh environments and can withstand significant physical damage. Fifthly, flexible metal conduit, or FMC, is a flexible metal conduit that is used to protect conductors in tight spaces or where movement is required. It is typically used for connecting equipment to a power source. Sixthly, liquid-tight flexible metal conduit, or LFMC, is a flexible metal conduit with a liquid-tight jacket. It is suitable for use in wet locations and can protect conductors from moisture and corrosion. Seventhly, cable tray is a system of metal trays that are used to support and route cables. It is typically used in commercial and industrial settings where there are a large number of cables. Eighthly, direct burial cable is designed for underground installation without the need for conduit. It has a heavy-duty jacket that protects the conductors from moisture and physical damage. When selecting a wiring method, it is important to consider the environment, the type of occupancy, the number of conductors, and the ampacity requirements. The NEC provides rules for selecting the appropriate wiring method for different applications. Proper installation of wiring methods is essential for ensuring a safe and compliant electrical installation. Grounding and bonding are essential components of electrical systems, providing safety and preventing electrical shock hazards. Grounding refers to connecting the electrical system to the earth, providing a path for fault currents to flow back to the source. Bonding refers to connecting all metal parts of the electrical system together, creating a low impedance path for fault currents. Firstly, the grounding electrode system consists of a grounding electrode conductor, a grounding electrode, and any bonding jumpers required to connect the electrode to the electrical system. The grounding electrode can be a metal rod, pipe, or plate buried in the earth, or it can be the metal frame of a building or concrete encased electrode. Secondly, the equipment grounding conductor, or EG, is a conductor that connects the metal enclosures of electrical equipment to the grounding electrode system. The EGC provides a low impedance path for fault currents, allowing the overcurrent protection device to trip and to energize the circuit. Thirdly, the bonding jumpers are used to connect metal parts of the electrical system together, such as metal conduits, metal enclosures, and metal equipment. Bonding jumpers ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock. Fourthly, the main bonding jumper is used to connect the grounded conductor, typically the neutral conductor, to the grounding electrode system at the service entrance. The main bonding jumper provides a path for fault currents to flow back to the source. Fifthly, separately derived systems, such as generators and transformers, require their own grounding electrode system. The grounding electrode system for a separately derived system must be installed in accordance with the NEC. Sixthly, grounding and bonding requirements vary depending on the type of occupancy, such as residential, commercial, or industrial. The NEC provides specific grounding and bonding requirements for different types of occupancies. Proper grounding and bonding are essential for ensuring a safe and reliable electrical system. Improper grounding and bonding can increase the risk of electric shock and can damage electrical equipment. The NEC provides detailed requirements for grounding and bonding, and it is important to follow these requirements to ensure a safe and compliant electrical system. Overcurrent protection devices, such as circuit breakers and fuses, are essential components of electrical systems, providing protection against overloads and short circuits. Overloads occur when the current in a circuit exceeds the ampacity of the conductors, causing them to overheat and potentially start a fire. Short circuits occur when there is a direct connection between two conductors with different potentials, resulting in a very high current flow. Firstly, circuit breakers are devices that automatically interrupt the flow of current in a circuit when an overload or short circuit occurs. Circuit breakers can be reset after the fault has been cleared, allowing the circuit to be restored to normal operation. Secondly, fuses are devices that contain a fusible link that melts and interrupts the flow of current when an overload or short circuit occurs. Fuses must be replaced after they have blown. Thirdly, the ampacity of an overcurrent protection device must be selected based on the ampacity of the conductors it is protecting. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and installation method. Fourthly, the interrupting rating of an overcurrent protection device is the maximum amount of current that the device can safely interrupt. The interrupting rating must be sufficient to handle the available fault current at the point of installation. Fifthly, the time current characteristic of an overcurrent protection device describes how quickly the device will trip in response to an overload or short circuit. Different types of overcurrent protection devices have different time current characteristics. Sixthly, overcurrent protection devices must be installed in readily accessible locations and must be protected from physical damage. The NEC provides requirements for the location and protection of overcurrent protection devices. Seventhly, overcurrent protection devices must be properly labeled to indicate their ampacity and interrupting rating. The labels must be legible and permanently affixed to the device. Proper selection and installation of overcurrent protection devices are essential for ensuring a safe and reliable electrical system. Improper overcurrent protection can increase the risk of fire and can damage electrical equipment. The NEC provides detailed requirements for overcurrent protection, and it is important to follow these requirements to ensure a safe and compliant electrical system. Electrical safety is paramount when working with electrical systems. It involves understanding potential hazards, using safe work practices, and wearing appropriate personal protective equipment. Firstly, always to energize electrical circuits before working on them. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, use insulated tools when working on electrical circuits. Insulated tools provide a barrier between the worker and the electrical current, reducing the risk of electric shock. Thirdly, wear appropriate personal protective equipment, or PPE, such as safety glasses, insulated gloves, and arc flash protective clothing. Safety glasses protect the eyes from flying debris, insulated gloves protect the hands from electric shock, and arc flash protective clothing protects the body from burns caused by an arc flash. Fourthly, never work on electrical circuits in wet or damp conditions. Water is a good conductor of electricity, and working in wet or damp conditions increases the risk of electric shock. Fifthly, be aware of overhead power lines when working outdoors. Maintain a safe distance from overhead power lines to avoid contact. Sixthly, use ground fault circuit interrupters, or GFCIs, in wet or damp locations. GFCIs protect against electric shock by detecting ground faults and interrupting the flow of current. Seventhly, inspect electrical equipment regularly for damage. Damaged equipment can pose a safety hazard and should be repaired or replaced. Eighthly, follow lockout-tagout procedures when working on electrical equipment. Lockout-tagout procedures ensure that the equipment is energized and cannot be accidentally energized while work is being performed. Ninthly, be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can cause severe burns and other injuries. Wear appropriate arc flash protective clothing when working on energized electrical equipment. Tenthly, seek training and certification in electrical safety. Proper training and certification can help you understand the potential hazards of working with electrical systems and how to work safely. Electrical safety is a shared responsibility. Everyone who works with electrical systems should be aware of the potential hazards and should follow safe work practices. By following these guidelines, you can help prevent electrical accidents and injuries.